Hi everyone. So in the last lecture we were discussing countability. We have already seen what are uh, I can say the revision of functions we have done and the definition of the definition of cardinality we have seen, right? Yes or no? So in this chapter, so far what we have done, we have seen the revision of functions, what is injective function, what is surjective function, what is bijective function, and what is the definition of cardinality if you want to compare sizes of two set. Okay, so remember cardinality, we use it to compare sizes of two set. You have two set, can you compare the sizes of these two set? Okay, so very simple. Now in this lecture we will study the definition of countable set and the definition of uncountable set. This is what we are going to study in this lecture. Okay, so story so far we have seen these concepts. We have seen the concept, the definition of cardinality. We have seen that the cardinality of set A that is equal to cardinality of set B if and only if there exists a bijection from A to B. Yes or no? This definition we have already seen, right? Cardinality of set A that is equal to cardinality of set B if and only if there exists a bijection from A to B. Okay, also we have seen that if there is an injection from A to B, then we will say that cardinality of A that is less than equal to cardinality of B. So these concepts so far we have seen. Yes or no? So these definitions we have seen so far. You have two set. These can be any set, finite, infinite. So you have two set, any set. They have same cardinality if and only if there is one-to-one correspondence between them. Okay, so this is the definition of, I can say, uh, this is the situation in which we can say that cardinality of A is equal to cardinality of B. Okay, so this is the idea. Now you can easily notice this is the definition. Now some very obvious results, you can check it out. Some very trivial consequences you can see. What are the trivial consequences? These are the trivial consequences. The first trivial consequence you can notice, if cardinality of set S that is less than equal to cardinality of set T and cardinality of T is less than equal to cardinality of set, let's assume P, then can I say cardinality of set S that is less than equal to cardinality of set P? Tell me. So this is very intuitive. You can see if cardinality of set S that is less than equal to cardinality of set T and cardinality of T that is less than equal to cardinality of P, then cardinality of S will be less than equal to cardinality of P. Okay, so this is quite intuitive result. You can easily notice. Okay, here you can see this is true. Also, this is also true that if cardinality of S that is equal to, if that is less than equal to cardinality of T and cardinality of T that is less than equal to cardinality of S. In this situation, what we can say, tell me? Means cardinality of set S that is less than equal to cardinality of T and cardinality of T that is less than equal to cardinality of S. Then in this situation, what you can say? In this situation, you can say that cardinality of S that is equal to cardinality of T, right? Yes or no? So very simple point. And the same thing you can say in the other direction also. In the other direction also, if two set have same cardinality, then what you can say? Then you can say that, I can say, then you can say this also and you can say this also. Okay, very simple. So all these points we have already seen. You can just check it out. Okay, all of them we have already seen. All these points we have already seen. Also, this is a fourth point, that if cardinality of S is equal to cardinality of T and cardinality of T is equal to cardinality of P, then in this situation, what you will say? You will say cardinality of S is equal to cardinality of P. So these are some, I can say, some trivial consequences. Okay, some very basic consequences. So these are the properties that this cardinality will satisfy. Okay, so I hope you understood all these things. So you can see. So remember, whatever two set I give you, for any two set, exactly one of the following will be true. Agree with me? Yes or no? If I give you any two set S comma T, then either this will happen or this will happen or this will happen. Exactly one of them will be true. You can notice exactly one of them will be true. If I give you any two set, then either their cardinality will be same or cardinality will of S will be less or cardinality of T will be less. So if I give you any two set, then exactly one of these will happen. Okay. Also, we have seen this. If you remember, when can I say cardinality of S that is strictly less than cardinality of T? When can you say this? When can I say this? This I can say if there exists a injection, but there does not exist a bijection. Yes or no? See, when can I say that cardinality of S is strictly less than cardinality of T? This I can say if and only if this I can say this and this. Okay, means there is injection from S to T, but there is no bijection from S to T. Yes or no? There is injection from S to T, but there is no surjection from S to T. Okay, so all these points actually we have seen. So you can just check it out. All these results, everything we have already seen. Okay, so this is the summary so far. So please tell me so far, are you comfortable? Are you comfortable with these concepts? Bijection, injection, surjection, also cardinality. These concepts, are you comfortable? All the results that we have seen. Okay, cardinality, bijection, injection, surjection, bijection, injection. Okay, so these are the concepts that you should understand. Okay, so far we have seen these concepts, and I hope you understood everything so far. Okay, now let's move on. Now let's move on. Now let's see the complete overview of this chapter. Okay, see, before telling you the definition of countable set, uncountable set, you might be thinking, sir, when can I say a set is countable? When can I say a set is uncountable? So before telling you the definitions of these set, I want to give you a complete overview of this chapter. Okay, then we will see one by one what are the definition of countable set, what are the definition of uncountable set. Okay, everything we will see, but before that I want to give you complete overview of this chapter. Okay, so before I tell you the overview also, okay, let's see one story. Let's see one story, the story of Georg Cantor. Okay, so this story I want to tell you. First of all, let me tell you very important, like this is something very interesting, that these concepts like countable set, uncountable set, understanding infinity, all these concepts were given by Georg Cantor. Okay, all these concepts basically in this countability, remember, in this countability whatever we study, everything is given by Georg Cantor. Is this clear? So you can see this complete chapter. This complete chapter is given by Georg Cantor. So let's see. I can say just let's get to know about this Georg Cantor. He has a very interesting story, I can say. So story of Georg Cantor. Let me tell you, he was a great mathematician. Okay. So this is Georg Cantor. You can see this is from 1870s and this is from 1910. Okay. So you can see this is Georg Cantor. Now what he did, let me tell you very interesting thing, that this is what he did. He invented this set theory. Okay. The set theory that we study, right? Yes or no? The set theory that we study, he invented set theory. He invented this concept of bijection. This concept of bijection he invented. Okay, the concept of bijection, what is one-to-one correspondence, the concept of bijection, he understood infinity. Okay, so he gave many, I can say many brilliant results he gave, and also he gave infinite hierarchy of infinities. This we will see, don't worry. Okay, all these things we will see, don't worry. Okay, so this is what he did. Now let me tell you that when he gave this infinite hierarchy of infinities, okay, at that point of time people did not believe it. Okay, see, mathematicians at that point of time in 1900, mathematicians, what they used to think, they used to think that infinity is infinity. You know, if two set are infinite, then they have same size. Yes or no? Because agree with me, at that point of time mathematicians, they used to think that if two set have infinite size, okay, you take any two set, if they are infinite, then they have same size. Yes or no? Agree or not? Okay, so this is what people used to think, mathematicians at that point of time in 1900. But what Cantor did, Cantor said that no, in the infinity also there are infinite levels. Okay, means some infinite sets are bigger than other infinite sets. This is what Cantor did. Okay, so Cantor basically did something that mathematicians did not know. Okay, so at that point of time, let me tell you, Cantor proved that within the infinity also there are infinite levels of infinity, means some infinite set they are bigger than other infinite set. Okay, so this is what Cantor did. Now let me tell you, When Cantor proved this, okay, when Cantor gave this, I can say this statement, when Cantor gave the proof, at that point of time, he also knew that mathematicians will not be happy. Okay, mathematicians will not be happy. So actually, you can see Cantor was well aware. Okay, at that point of time, Cantor was well aware that this opinion, okay, what he is going to do, you can say, okay, what he has given, what he has, I can say, invented, that will not make mathematicians happy. He knew this. Okay, so basically he said that my opinion, they don't go with the, I can say, typical opinion, okay, about infinity, about the nature of infinity. Okay, basically Cantor said that mathematicians at that point of time, they did not understand infinity. Okay, so this is what basically Cantor did. Okay, at that point of time, mathematicians, their understanding of infinity was not correct, I can say. Okay, so let me tell you what happened. The same thing happened, that mathematicians were not happy. Okay, they were really not happy. And basically what they did, they they, I can say, they opposed him. Okay, at that point of time, mathematicians, his fellow mathematicians, they did not see, I can say, they thought that this country is lying, they thought that this country is doing, I can say, unnecessary, I can say, unnecessary things. Okay, so at that point of time, he faced a lot of backlash, and he went into depression. Okay, so actually his professor himself, let me tell you, okay, his professor himself did not agree with his, I can say, with his paper. Okay, see, so this Cantor, he published a paper, and when he published the paper, his professor himself was not, I can say, was not happy. And this professor called him scientific charlatan, you can see, or corrupter of youth. Okay, so these things he called. And let me tell you, many great mathematicians at that point of time, they called him grave disease. Okay, you can see, they called that Cantor's ideas are grave disease. So because of this type of backlash, you can see Cantor quit the mathematics. Okay, Cantor gave up mathematics. Cantor went into depression, let me tell you, and he gave up mathematics. And then finally, after some time, he died also. Okay, so basically he lived in poverty, and he died also because of this depression, I can say, he died also. Okay, so this is the life of George Cantor. Now let me tell you that after he died, okay, after, I can say, after a few years after he died, okay, then people started realizing how great his work is. Okay, the, I can say, the significance of his work, that was realized after he died. So you can see there were many mathematicians, they called him, you can say, they called him the finest product of mathematical genius. Okay, so this is what happened after George Cantor was gone. Okay, so this is the life of George Cantor. I just want to tell you one thing, that when he was alive, at that point of time, mathematicians, they did not realize how significant his work is. Okay, the significance of his work was realized after few years. Okay, so very simple. And today, this George Cantor, he is known as among the great mathematicians. You can see the set theory that we study, that is given by George Cantor. And nowadays, all the concepts that we study, these are basically given by George Cantors. Okay, so basically today, what we understand infinity, that was given by George Cantor. Okay, at some point of time, you can see there was a different understanding of infinity, but now today we understand infinity in a different way. Okay, and that was given by George Cantor. So this is the life of George Cantor. You can see, now people call him, I can say, a great genius. Okay, so this is the work of, I can say, George Cantor. I hope you basically liked the story of George Cantor. So anyway, now let's see what George Cantor did. What he did, George Cantor, what he did basically. Okay, let's see that. Okay, so what George Cantor did, that is the main part that we want to focus on. So let's see what George Cantor did. Okay, so George Cantor, he proved that there are infinite levels of infinity. Within the infinity also there are infinite levels. Within the infinity also there are infinite level. Means some infinite sets, they are bigger than other infinite sets. This is what George Cantor did. Let me tell you. Okay, George Cantor, he proved that if you see all the infinite sets, if you look at all the infinite sets, let's assume these are all the infinite sets. Okay, let's assume these are all the infinite sets. In these infinite sets also there are levels. Okay, the lowest level he called countable set. Okay, remember I am talking about infinite sets. Okay, if you look at all the infinite sets, in the infinite sets, the lowest level he called countable infinite. What he called? He called countable infinite sets. The lowest level, countable infinite sets. This is the lowest level, let me tell you. Okay, and he named it the lowest level. He called it countable infinite sets, and he denoted this by this symbol. Okay, this was a symbol he used. So you can see this type of symbol, LF0. Okay, this type of symbol was used. So you can see this type of symbol, LF0. Okay, anyway, so don't worry about the symbol. But I'm saying that this is what Georg Cantor did. He said that among the infinite set, if you see all the infinite set, then you can see that the lowest level he called countable infinite set. Okay, and let me tell you, in this countable infinite set, in this lowest set, let me tell you, you have your set of natural number, your set of integers, your set of whole numbers. These things are here. Okay, on the lowest level, these things you have: set of natural numbers, set of integers, set of whole numbers. Okay, but there are other levels also. Actually there are infinite levels. Actually there are infinite levels, and we will prove it, don't worry. We will see this in the next lecture. We will see that we will also prove that there are infinite levels of infinity. Okay, we will see the proof that Cantor gave. Okay, Cantor gave a proof, and that proof also we will see. But this is interesting, right? That there are infinite levels of infinity. For example, you can see at the lowest level you have these set, like set of natural number, set of integer, set of whole number. All these, they are on the lowest level, but there are another levels also. For example, if some set is here, let's assume. Okay, see, actually let me tell you, we will prove it. Don't worry about it right now. But actually 2 power n means power set of n, means power set of n. 2 power n, what that means? That means power set of n. Let me tell you, that is here, means that is this power set of n, that is more infinite than set of natural number. Means this set, the size of this set is bigger than the size of natural numbers. Okay, power set of n, that has bigger size than set of natural number. Okay, so like this he created basically infinite levels he created. Okay, like this he created infinite levels of infinity. All of them you can see, all these are infinite levels of infinity. Is this clear? This was very interesting result, that infinity also has infinite levels. For example, this set, the size of this set is smaller than this set, or I can say this set is bigger than this set. Okay, similarly there is a set here which is bigger than this set. Similarly there is a set here which is bigger than this set. Yes or no? This set is bigger than this set. This set is bigger than this set, and this set is bigger than this set. And the lowest level, on the lowest level you have set of natural numbers, set of integers, set of whole numbers. The lowest level is called countable infinite set. Okay, so this is the idea. I hope you understood this. This is the overview. Did you understand? Please tell me. This is the overview. You can see that Cantor proved that there are infinite levels of infinity. Okay, and what he did, the lowest level of infinity he called countable infinite. The lowest level of infinity, that is called countable infinite. Okay, so this is the infinite levels of infinity. So I hope you understood. Okay, so don't worry, all these things will become more and more clear. Okay, so in the last lecture we have seen that cardinality of whole numbers, that is same as cardinality of integers, right? This is what we have seen. In the last lecture. In the last lecture we have seen the cardinality of whole numbers, that is same as cardinality of integers. In this lecture we will see that cardinality of whole numbers, that is same as cardinality of natural numbers. This is what we will see in this lecture. Okay, and let me tell you, all these set, they are the lowest level of infinity, all of them. Okay, all these, like set of whole number, set of integers, set of natural number, set of even natural number. Okay, all these are the lowest levels of infinity. These are the lowest levels of infinity, lowest level of infinity. Is this clear? Okay, and these are called the lowest level of infinity. This lowest level of infinity, this is called countable infinite. This is called countable infinite. Is this clear? Okay, this is the overview. This is just an overview. Don't worry, we will revisit this. Okay, we will again see this. We will give the proof. I will give you the proof that there are infinite levels of infinity. This proof I will give you. This is a very interesting proof. Okay, so all these things we will revisit, but this is the overview. Please tell me, did you understand? So you can see what Cantor did. You can just check it out here. So Cantor basically gave a hierarchy of infinite numbers, unlimited hierarchy of infinite numbers. Okay, you can see so infinite levels of infinity. This is what he gave. Okay, some infinite, some infinite set, they are bigger than other infinite set. You can see some infinities are more infinite than others. Okay, so this is what I can say Cantor did. I hope you understood this overview. Please tell me, did you understand the overview? Let me know. This is just an overview. Don't worry. Everything we will again see. What is countable set? What is uncountable set? The definition, the analysis, the proof, everything we will see, okay, in the future. But this is just an overview, nothing else. Now let's see the definition of countable set. Now our next chapter, that is countable set. What is the definition of countable set? Let's see. So let's see the definition of countable set. Countable set means a set which is either finite. You can see this is the definition of countable set. A set which is either finite or has the same cardinality as set of positive integers, that is called countable. That is called countable. And if a set is not countable, then that is uncountable. Okay, see, this is the simple point. What is the definition of countable set? Countable means every finite set is countable. Okay, see, let me tell you what is a countable set. What is a countable set? This countable set, I can say every finite set is countable. Okay, this can be countable also, finite also. Countable set, it can be finite set also. Okay, remember every finite set is countable. Okay, every finite set is countable. If you take any finite set, every finite set is countable. Is countable. Okay, this is the first point, that every finite set is countable. And the second point, if you see the infinite set, when can I say infinite set is countable? Infinite set is countable if that has the same cardinality as set of natural numbers. Okay, infinite set S, I can say infinite set S is countable. When can I say infinite set S is countable? If and only if the cardinality of S, that is same as cardinality of natural numbers. Okay, so this is the definition. Did you understand the definition? Please tell me. The definition of countable set is very simple. A set S is countable. When can I say a set S is countable? When can I say a set S is countable? If and only if S is either finite, okay, S is either a finite set, or okay, S is either a finite set, or tell me, or has the same cardinality as set of natural numbers. The cardinality of S, that is same as set of natural numbers. Okay, this is the definition of countable. Is this clear? The definition of countable is that clear. The countable set, you can see every finite set is countable. And I can say if your set is infinite, then when can you say S is countable? S is countable if it has the same cardinality as set of positive integers. This is the definition. Read this. A set is either finite. When can you say a set is countable? Either it is finite or it has the same cardinality as set of positive integers. This type of set will be called countable. And if a set is not countable, then that will be called uncountable. So this is the definition of countable set. I hope you understood. So remember, countable set, it can be finite also, it can be infinite also. Every finite set is countable. That is a very simple point. Every finite set is countable. Also remember, when can I say infinite set will be countable? When can I say infinite set will be countable? You can see infinite set S will be countable if it has the same size as set of natural numbers. Okay, so this is the definition. This is the definition of countable set. I hope you understood. Let's see some examples. But before that, you tell me a simple question I'm asking. If you know that S is infinite, okay, if S is infinite and countable, okay, if S is infinite and countable, what you can say about S? What can you say about the size of S? If S is infinite and countable, then what you can say about the size of S? What can you say about the size of S? Tell me. Size of S, that will be same as size of natural numbers. Yes or no? Correct? If S is infinite and S is countable, in this situation, I can say size of S, that will be same as size of natural numbers. Okay, very simple. If S is both countable and infinite, then there is a bijection between S and N. You already know the definition of this. You already know what is the definition of this statement. This simply means what? This simply means there exists a bijection. Yes or no? This means there exists a bijection between S and N. This you already know. Okay. So please tell me, is the definition of countable clear? Definition of countable, is that clear? Remember this countable set, that is the lowest level of infinity. Let me tell you, this countable set, I can say this countable infinite, this countable infinite, this countable infinite is the lowest level of infinity, is the lowest level of infinity, lowest level of infinity. This countable set, this is the lowest level of infinity. This is the lowest level of infinity. So tell me, if this is the lowest level of infinity, okay, just think about it. Countable infinite. Remember, I am talking about countable infinite. Countable infinite is the lowest level of infinity. So if this is the lowest level of infinity, then this type of set is possible or not? For example, this countable infinite, you already know what is countable infinite. Every set which has same size as, what is countable infinite? Tell me. When can you say a set is countable infinite? When it has the same size as set of natural numbers. Yes or no? When it has the same size as set of natural numbers. Okay, the size must be set of natural numbers. Correct? Now you tell me, if this is the lowest level of infinity, I am saying this is the lowest level of infinity. So is there any set? Is there any infinite set as such that set S cardinality is strictly less than set N cardinality? Is there any such set? Tell me. I am asking, this type of set exists or not? Is there any infinite set? Is there any infinite set whose cardinality is less than cardinality of N? Is there any such infinite set? Is there any such infinite set? The answer is no. Yes or no? The answer is no, because this countable infinite, this is the lowest level of infinity. Is this clear? This is the lowest level of infinity. So remember, if you see the levels of infinity, the lowest level of infinity is this. The lowest level of infinity, that is where your set of natural number is there. Okay. So anyway, let's see some practice. Let's do some practice. Let's prove that whole numbers are countable. Let's prove that whole numbers are countable. Okay. So how to prove it? Tell me. What you will do if you want to prove it? If you want to prove set S is countable, what you want to do? Tell me. I want to prove that set of whole numbers is countable. What to do? First of all, set of whole numbers is infinite. Yes or no? First of all, set of whole numbers, you already know this is infinite set. This you already know that this is infinite set. Okay, this is infinite set. Now, how to prove that this is countable? What you will do? What you will do? Tell me what to do. If you want to prove, then what to do? Simple question I'm asking. If you want to prove, then what to do? Very simple. Just prove that the cardinality of W, that is same as cardinality of positive integers. Yes or no? And how to do that? That will be done by, there exists a bijection. If you can create a bijection, between set of whole numbers and set of natural numbers, can you create a bijection? Can you create a bijection? Okay, see, very simple. Can you create a bijection between set of whole numbers and set of natural numbers? So this is your set of natural numbers and this is your set of whole numbers. Can you create a bijection between them? For example, these are the natural numbers 1, 2, 3, 4. These are the positive integers and these are the whole numbers 0, 1, 2, 3, 4 and so on. Can you give me a bijection? Can you give me a bijection from N to W? Can you give me a bijection F? Let me know. Anyone? Can you give me a bijective function? Can you give me one-to-one correspondence? Can you give me one-to-one correspondence between positive integers and whole numbers? Can you give me a one-to-one correspondence? Yes. Consider this one-to-one correspondence. Consider this one-to-one correspondence, right? Just consider this one-to-one correspondence. Okay, so you can easily see, I can give you from positive integers to W, I can give you this. F of n is equal to n minus 1. Yes or no? F of n is equal to n minus 1. Can you check this is injective? This is 1, 1 also. This is on to also. Yes or no? This is 1, 1 also. This is on to also. So this is bijection. This is actually bijection. This is actually bijection. So there exists a bijection. You can notice this is 1, 1. See, this is one-to-one correspondence, right? Yes or no? You can see. Because this is 1, 1 also. This is on to also. Two different elements. Do they have different images? Different elements. Different elements. Will they have different images? Yes, of course. Yes or no? Different elements will have different images. If you have some element x here, then the image will be x minus 1. Different elements have different images. So this is 1, 1. And you can notice every element is covered. Every element is covered. For example, if you take some element t here, what the pre-image? What is the pre-image? If you take some t element t here, then what will be the pre-image? The pre-image will be t plus 1. Pre-image will be t plus 1. Yes or no? Okay, very simple. I hope you understood. So you can see this is on to also. So this function, you can see this function, this is on to also, 1, 1 also. So this function is bijection. And because there exists a bijection, so what I can say? Tell me, from set of natural numbers to set of whole numbers, you can see fn equal to n minus 1. You can easily notice this. This f is a bijection. F is a one-to-one correspondence. One-to-one correspondence. So because there exists a one-to-one correspondence, what you can say? There exists a one-to-one correspondence. So in this situation, what I can say? So I can say this whole number. Okay. Or I can say that they have same cardinality. Their cardinality is same. Yes or no? So their cardinality is same. And if these two have same cardinality, the cardinality of W, that is same as cardinality of positive integers. This is the definition of countable. Yes or no? So in this situation, I can say W is countable. Agree with me? In this situation, I can say W is countable. This is the definition of countable infinite. So I can say W is basically countable infinite. Is this clear? Please tell me. Let me know, did you understand? This is the proof. We have proved that set of whole numbers is countable. We have proved that set of whole numbers is countable. Remember the definition of countable and the definition of countable infinite. What is the countable definition? Countable definition and countable infinite definition. What are these? Countable infinite definition. Because remember this point, I told you countable can be finite or infinite. Yes or no? What is the definition of countable and countable infinite? When can I say S is countable? Please tell me. When can I say S is countable? S is countable if and only if cardinality of S is less than equal to cardinality of N. Agree with me? Because S can be finite also. Because S can be finite also. Okay, because S can be finite also. And when can I say S is countable infinite? And when can I say S is countable infinite? Tell me. And when can I say set S is countable infinite? If and only if set S cardinality is same as set N cardinality. Yes or no? Is this clear? Because remember this point, that countable can be finite also. Countable. There are two type of countable set. Countable set, every finite set is countable. Every finite set is countable. Okay. Or countable infinite. Or countable infinite. Okay. Or countable infinite. Is this clear? So you can see every finite set is countable. If you have a finite set, S, then can I say this cardinality is less than the cardinality of set of natural numbers? Tell me, can I say? If you have a finite set, can I say the cardinality of set S? Cardinality of set S that is less than equal to, that is less than cardinality of set N. Actually, what this means, please tell me. In terms of injection bijection, what this means? Let me know. What this means in terms of injection bijection? This means there is injection from S to N, but there is no bijection between S and N. Yes or no? There is injective function from S to N, but there is no bijective function between them. So this is what happens in finite set. And what about countable infinite? What about countable infinite? That has same size as set of natural numbers. Yes or no? Is this clear? So you can see countable set that can be finite or infinite. Every finite set is countable, and you can see. And when can I say an infinite set is countable? Infinite set is countable if it has same size as set of positive integers. So this is the definition of countable. You can see S is countable if and only if there is a injective function from S to N. Yes or no? S is countable. S is countable. When can I say S is countable? Tell me. When can I say S is countable? Let me know. Just tell me the definition. S is countable if and only if. What this means? This means there exists an injective function from S to N. There exists an injective function from S to N. From S to N. There exists an injective function from S to N. Then we can say that S is countable. This is the definition of countable. Okay, let's move on now. Now let's see the next question. Prove that set of positive even integers is countable. How to prove that? I want to prove that set of positive even integers, that is countable. This set of positive even integers. Let's prove this is countable. How to prove this is countable? To prove E is countable, what we need to do? To prove E is countable, what we need to do? Tell me. What we need to do if you want to prove E is countable? Remember, this is already infinite, right? This is already infinite set. This you already know. So tell me, this E is countable. How to prove it? Remember, this E is already infinite. This E is already infinite. So how to prove this infinite set is countable? If you want to prove it, then just prove that the cardinality of E that is same as cardinality of positive integers. Yes or no? Just prove this. This is what you need to prove. And if you want to prove this, then what you need to give? You need to give there exists a bijection. There exists a bijection between E and N. There exists a bijection between E and N. So tell me what to do now. Can you give me bijection? Can you give me a bijection between N, comma E? So yes, I can easily give you bijection. Okay. See what you can do. This is your set of natural number. 1, 2, 3, 4, 5, 6. Okay, and so on. This is your set of even positive even integers. This is set of even positive integers. You can see. Okay, so tell me which bijection you will give. Let me know which bijection you will give. Give me a one-to-one correspondence between set of positive integers and set of even positive numbers. Now tell me. Give me a one-to-one correspondence. Yes, you can give me this. This one-to-one correspondence you can give me. This one-to-one correspondence you can give me means you can give me Fn equal to 2n. Fn equal to 2n. You can easily notice this is 1, 1 also. This function, this is 1, 1 also. And this function is on to also. You can easily see. So this function, this is bijective. So F is bijection. So F, that is bijection. Yes or no? And because there exists a bijection, since there exists a bijection between these two, there exists a bijection between set of natural number and set of even, I can say even positive integers. Then what I can do? Because there exists a bijection, so what I can do? Tell me what I can say. I can say they have same cardinality. I can say they have same cardinality, right? Yes or no? And that simply means that E is countable. That simply means E is countable infinite. E is countable infinite. Is this clear? Please tell me. Let me know. So this is a very simple idea. This is how you can prove a set is countable or not. Okay. Let's see this question. Tell me the answer for this question. How to prove? I want to prove that set of odd positive integers is countable set. How to do that? Set of odd positive integers, that is countable set. Let me know how to do that. First of all, if you want to prove it, what you need to prove? If you want to prove this set of odd positive integers, let's assume this is your S. That is odd positive integers. That is 1, 3, 5, 7, and so on. Okay. So if you want to prove this, then what you need to do? Tell me. You already know this is infinite. You already know this is infinite set. This you already know. So if you want to prove that this is countable set, all you have to do, just prove that the cardinality of S, that is same as cardinality of N. Okay. And if you want to prove this, then you just have to give a bijection. Just give a bijection. Give a bijection between set of natural numbers and set of S. Yes or no? This is what you need to do. Just give a bijection. Can you give me a bijection? Can you give me a bijection? This is N, this is S. Okay, 1, 2, 3, 4, 5, 6, and so on. This is N. And what is S? S is like this: 1, 3, 5, 7, 9, 11, and so on. So tell me, can you give me a one-to-one correspondence between these two? Between these two set, can you give me a one-to-one correspondence between these two set? Yes, just give me this one-to-one correspondence. Just consider this one-to-one correspondence, right? Yes or no? Consider this one-to-one correspondence from N to S. Consider this one-to-one correspondence. What is Fn? What is Fn here? That is 2n minus 1. That is 2n minus 1, right? Yes or no? Can you notice this function? Can you check this function is 1, 1 also? This function is on to also. This function is 1, 1 also. This function is on to also. So remember, this function is bijection. So this function is bijection. And because there exists a bijection, and since there exists a bijection, between N comma S, so what you can say? And this S is already infinite. And this S is already infinite. So because there exists a bijection, so what I can say? I can say they have same cardinality. Yes or no? The cardinality of positive integers, that is same as cardinality of odd positive integers. Okay, so this is what we have. And from here, you can easily notice that from here, you can say S is countable. S is countable infinite. S is countable infinite. Is this clear? Please tell me. Let me know. Did you understand? So far, everything that we have done. Please tell me. Did you understand? Let me know. Is this clear? Okay. So did you notice one thing? That so far what we have done? So far what we have done? We have proved that set of whole numbers, the size of set of whole numbers, that is same as size of natural numbers. Yes or no? We have proved this, that they have same size. These two sets, they have same size. We have done this. We have also proved that set of natural number, that size is same as set of even positive integers. This also we have proven. Set of natural numbers, that is same as set of odd positive integers. So basically these are the some things that we have done. Yes or no? All of them, they have same cardinality. All of them, they have same cardinality. Means they have I can say same size. All of them, they have same size. Let's see this question. Prove that integers are countable. How to prove this? I want to prove that integers are countable. How to prove this? Let me know. I want to prove that integers are countable. Now, how to do that? See, let me tell you very interesting proof. Of course, you can give a bijection, but do you need to give a bijection? See, of course, you can give a bijection, but do you need to give a bijection? Tell me, this is my question. See, this is my question. See, you already know this, that if I want to say S is countable, when can I say? Set S is countable. When can I say set S is countable? When can I say set S is countable? If and only if set S is countable, if and only if cardinality of S is less than equal to cardinality of natural numbers. Yes or no? This you already know. Agree with me? Please tell me. Set S is countable if and only if cardinality of S is less than equal to cardinality of N. Yes, correct. Now what this means? Let me know. What this means? What this means? Please tell me. What this means? This means there exists an injective function. There exists an injective function from S to N. From S to N. So basically, you just have to give an injective function, right? Yes or no? You just have to give injective function. Agree with me? So remember, this is what you can do. Okay, now what you can do to prove S is countable. To prove set S is countable. Set S is countable. What you can do? To prove set S is countable, there are many different methods. See, if you want to prove set S is countable, what you can do? First thing, if S is finite, can I say it is countable? If S is finite, can I say it is countable? If S is finite, can I say it is countable? Then S is countable, right? Yes or no? If S is finite, then S is countable. This we already know. What is the second method? If S is infinite, then what to do? If S is infinite, what to do? Okay. If S is infinite, then what should happen? If S is infinite, then this should happen. Okay, we need to prove this. Then we need to prove this. Okay, we need to prove this. And if you want to prove this, then you have to give a bijection. There exists a bijection. There exists a bijection between S and N. You need to give a bijection. Okay, but actually, what you can do, in simple words, you can simply say that S is countable if and only if. To prove S is countable, all you need to do, just create injective function. Just create injective function from S to N. Yes or no? Do you agree that just create injective function from S to N? If you want to prove that S is countable, set S is countable. If you want to prove set S is countable, because you know this, you know S is countable means what? S is countable if and only if. S is countable if and only if the cardinality of S, that is less than equal to cardinality of N. And you already know what this means. This means there exists an injective function from S to N. Okay, this means there is an injective function from S to N. So this is the complete idea. Okay, now if I want to prove integers is countable, can I just give an injective function from integers to natural numbers? Yes or no? This is method number one. What is method number one? Method number one, just create injective function. Can you create forcefully? You create an injective function. An injective function from where to where? Please tell me. From where to where? Just create an injective function. You create. I want to prove integers are countable. I want to prove that integers are countable. This is what I want to prove, that integers are countable. So tell me what I need to do. I need to create an injective function from where to where? From where to where? From integers to natural numbers. Yes or no? From integers to natural numbers. Very good. Like you can see here. Please notice. If you want to prove set S is countable, then you need to see this. S is countable if and only if this will happen. S is countable if and only if this will happen. Means there exists an injective function from S to N. So I want to prove integers are countable. So just create injective function from Z to N. Can you create injective function from Z to N? From Z to N, can you create injective function? Forcefully, any injective function will work. Just give me injective function. Remember, your target is what? Your target is to just give me injective function. I don't care about surjective. Just give me injective function. Just give a injective function. Just give an injective function from Z to N. From Z to N. Okay, just give an injective function, remember. I don't care about surjective. I just care about injective. Just give me injective function. Injective function means different elements, different images. Yes or no? Injective function, what that means? That means different elements, different images. Just make sure that different elements have different images. Just make sure different elements have different images. This is what you have to make sure. Different elements have different images. Just make sure this. You only have to make sure that different elements have different images. Can you give me? Can you give me injective? Yes, I can easily give you injective. See what I can do. Notice what I can do. I can simply do this. In your integers, what you have? These are the integers that you have, right? Like for example, you have 0, you have these integers, and you have these integers, -1, -2, -3, and these. Okay, I want to make sure that they get different images. Just give them different images. I want to make sure they get different images. Different elements get different images. This is what I want to make sure. I want to make sure I get injective function. So what I can do? This is quite simple. All of them you map to 2 power 0. Okay, all of them you map to 2 power of 2. Are you getting my point? All of them you map to power of 2. And where you will map these negative numbers? Where you will map these negative numbers? You map them to power of 3. You map them to power of 3. Is this clear? Now tell me. See, these will be even numbers. You cannot, these are the even images. All of them. Like from here, these are the even images. No one is matching, yes or no? Can you notice? Please tell me. Did you get injective function or not? See what I have done. Very simple. I just want to create injective function. Just give me injective function from Z to N. Don't think too much. Don't think too much. Just give me injective function from Z to N. Injective function means different elements, different images. So this is your set of integers. Just make sure that different elements get different images. So what you can do? These numbers you can map to power of 2. These numbers you can map to power of 3. Let me know. Any two images are same or not? Let me know. Any two images, they are same or not? Please tell me. Like for example, this is 1. All these will be even. All these will be odd. Any two images are same or not? Let me know. Any two images, they are same or not? Agree? Yes or no? Please tell me. Agree? So this is the point. Did you understand this? This is just a clever method. See why this is clever, let me tell you. Because you don't have to think too much. You don't have to create a bijection. You don't have to create a bijection. You just have to create some injection. You just have to create some injective function. You just have to make sure different elements get different images. You just have to make sure different elements get different images. In this set, different elements should get different images. So what I'm doing? Very simple. All these numbers I'm mapping to power of 2. All these numbers I'm mapping to power of 3. So this mapping, finally I'm getting this mapping. Remember what I have done? I have done this mapping from integers. These are the integers and these are your set of natural numbers. What I have done? This is what I have done. 0, 1, 2, 3, 4 and so on. Then you have -1, -2, -3 and so on. Okay, what I have done? Basically, this is what I have done. I'm mapping it to 2 power 0. All these numbers I'm mapping to power of 2. Power of 2. I'm mapping to power of 2. And all these numbers I'm mapping to power of 3. Yes or no? I'm mapping to power of 3. Correct? Tell me, is this surjective? This function that I have created a function. This function that I've created, is this surjective? I have created a function from Z to N. This is not surjective, but I don't care about surjective, right? Yes or no? This function that I've created, this is injective. This is injective. And because this is injective, so what that means? That means integers, size of integers is less than equal to size of natural numbers. Yes or no? Size of integers is less than equal to size of natural numbers. Size of integers is less than equal to size of natural numbers. Now you tell me. So what we have done? So we have proved that size of integers that is less than equal to size of natural numbers. And we know integers is infinite. And we know integers is infinite set. Now from these two things, what you can say? From these two things, what you can say? Remember, countable. This is the lowest level of infinity. Lowest level of infinity. So tell me, from these two things, what I can say? From these two things, what I can say? Tell me. I can say that integers have the same size as natural numbers. Integers have the same size as the natural numbers. Yes or no? Please tell me. Did you understand this? Let me know. Is this proof clear? Is this proof clear to everyone? Let me know. Did you understand this proof? We want to prove that integers are countable. All we have to do, remember, this is what we want to do. This was our question. Prove that integers are countable. So if I want to prove that integers are countable, I can just create an injective function from integers to natural numbers. And this is what I have done. I have created I can say injective function from integers to natural numbers. Injective function I have created. You can see. Okay, this function that I have created, this is injective function. Is this clear? Let me know. So this function that we have created, see, we have created this type of function from integers to set of natural numbers. I have created this type of function. This type of function I have created. If n is greater than equal to 0, what the image? If n is greater than equal to 0, what was the image? What was the image? The image of 2, the image was 2 power n. And if n is less than 0, what was the image? If n is less than 0, what was the image? That was 3 power minus n. Yes or no? That was 3 power minus n. Okay, for example, f of minus 3, what f of minus 5, what is that? That is 3 power 5. And that is same as 3 power minus of minus 5. That is 3 power 5. Yes or no? This function I have created. You can see this is injective function. This function I have created, you can notice this is injective function. We have created injective function. And because this is an injective function, so I can say that this will happen. Integers, size of integers that is less than size of natural numbers. But you can see, you know that integers are infinite set. So from these two, if you combine these two things, then you will get this. Please tell me, did you understand? Let me know. Is this point clear? Is this proof clear? Okay. So this is what we have done. Remember what you can do. What is the method to? If you want to prove that Z is countable, what is the method to? What is the method to prove Z is countable? To prove Z is countable, what is method 2? Create a bijection. Create a bijection, yes or no? If you want to prove Z is countable, what is the method 2? The method 2 is basically create a bijection. Create a bijection between natural numbers and integers. Between natural numbers and integers, create a bijection. This is what you can do. Okay, is this clear? And that also you can do, no problem. That is also not a big thing. You can create a bijection also. Okay, what you can do from between set of natural numbers and integers, can you create a bijection? Let me know. These are the set of integers. These are set of natural numbers. Can you create a bijection? Yes, you can create a bijection like this. -2, 2, -3, 3, -4, 4, and so on. And this is your 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. So you can, what you can do, you can give this one-to-one correspondence. This one-to-one correspondence you can give. This one-to-one correspondence you can give. What you can give? You can give this one-to-one correspondence. Okay, so tell me what is this function? Let me know what I have done. In this one-to-one correspondence, what I have done? See, I have done this. From integers to natural numbers, I have created this type of function, fn equal to, tell me if n is greater than equal to 0, what is happening? What is the image? If n is greater than equal to 0, what is the image? If n is greater than equal to 0, what is the image? Let me know. For example, if n is greater than equal to 0, what is the image? Let me know. That is 2n plus 1. Yes or no? Very good. Very good. Okay, then the image is 2n plus 1. Image is 2n plus 1. If n is less than 0, what is the image? If n is less than 0, what is the image? Let me know. If n is less than 0, for example, these, then that is minus of 2n. Very good. Very good. Minus of 2n. Minus of 2n. Okay, this is the function that we have created. You can just check it out. This is a 1, 1 also. This is 1, 1 also. And this is on 2 also. You can check it out. Tell me why this is 1, 1. Notice why this is 1, 1. Tell me, how can you say this is 1, 1? How can you say this is 1, 1? Because you can notice here you are getting even images. Here you are getting even images, right? Yes or no? See, this will give you even images. And this will give you odd images. This will give you odd images. So they do not overlap. Yes or no? They do not overlap. Correct? Even images, odd images, they do not overlap. They never overlap. Okay, so this is what I'm saying, that this is 1 1 also, and you can easily see that this is on 2 also. So this function is bijection. This function is bijection. And because there exists a bijection, so what you can say? Because there exists a bijection, since there exists a bijection between Z and N, since there exists a bijection between Z and N, so what you can say? Your bijection between Z and N. So I can say that they have same size. They have same size. And if they have same size, that simply means Z is countable. That simply means Z is countable. Okay, is this clear? Let me know. Please tell me. Okay, so very simple. Now tell me one more thing. I just want to give you another method. This final method I want to give you, method number 3. We want to prove that Z is countable. We want to prove Z is countable. One last method. In this method, what we are going to do, we want to prove Z is countable. Do you remember in the last class, we have proved that there is one-to-one correspondence between whole numbers and integers? Do you remember? Do you remember in the method number 3? See, in the last class, what we have seen in previous lecture, in last lecture, what we have seen, tell me. If you remember, in last lecture, we have seen that they have same cardinality. Do you remember? Do you remember? We have already done this. Set of whole numbers and set of integers, they have same size. In the last lecture, we have done this. We have already done this. And in this lecture, what we have done? In this lecture, what we have done? In this lecture, we have done that these two have same size. So from these two, what I can say? From these two, what I can say? I can say they also have same size. Yes or no? They also have same size. So I can say Z is countable. So Z is countable. Okay. Do you remember in the last class we have seen this set of whole numbers and integers? Do you remember this proof? If you remember, we have seen this. If you remember, set of whole numbers. This was your set of whole numbers. Set of whole numbers and integers, they have same size. This we have seen in the last class. This we have seen in the last class. This we have seen in this class. Okay, so finally I can say that integers and natural numbers, they have same size. Integers and natural numbers, they have same size. So Z is countable. So like this you can do. A lot of methods you have. Different methods you have. So finally, at this point of time, did you notice so far what we have done? So far what we have done, we have proved that set of whole numbers that has the same size as set of natural numbers, that has the same size as set of integers, that has the same size as set of even integers, like this. Okay, so like this, all these things we have done, that all of them have same size. This is what we have proved. Let's see one last example. Prove that set of non-negative integer powers of 2 is countable. How to prove it? Prove that set of non-negative integer powers of 2. Set of non-negative integer powers of 2. Let's call this set, let's call it set P. Let's call it set P. So what you have in this set? In this set, you have 2 power 0, 2 power 1, 2 power 2, 2 power 3. You have this. Now tell me, how to prove this P is countable? To prove P is countable, what do you need to do? If you want to prove P is countable, if you want to prove P is countable, then what you need to do? You already know P is infinite, right? This P is infinite set that you already know. So how to prove an infinite set is countable? How to prove infinite set is countable? To prove infinite set is countable, what you need to do? You need to prove that this has the same size as integers. I can say this has the same size as positive integers. This is what we need to prove. Yes or no? This is what we need to prove. Agree with me? We need to prove this. And we can do like this. See, what we can do in easy way, we can do this. First, we will prove that this happens. Okay, if you can do this, okay, prove it. This is what you prove. Then we have already proved this. We have already proved this. From these, can I say that they have same size? Yes or no? See, first we will do this. This we have already done. So finally, I can say they have same size. Okay, and how to do this? How to do this? Tell me. This P and W. Can you create a bijection between them? this p is 2 power 0, 2 power 1, 2 power 2, 2 power 3, and so on. And this is your w, 0, 1, 2, 3, and so on. So very simple, this bijection you can give. You can give this bijection from w to p. You can give this bijection fn is equal to 2 power n. This bijection you can create, yes or no? This bijection you can create from w to p. Okay, this is a bijection. This is a bijection. And because this is a bijection, so I can say what? I can say set of whole numbers, size of set of whole numbers, that is same as size of p. Okay, and we already know this. These we have seen. This we already know. So finally I can say what? Tell me. So I can say size of p, that is same as size of w. And we know, we already know that size of w is same as size of n. So tell me, from these two equations, what you can say? Equation number 1, equation number 2. What you can say from equation number 1, equation 2? From equation 1 and 2, what you can say? I can say set of cardinality of p, that is same as cardinality of n. That's it. This means p is countable. This means p is countable. Yes or no? Is this clear? This means p is countable. Okay. I hope you understood this method. So very simple. In the last class, we have already seen this, that w comma p, they have bijection. W comma p, they have bijection. This we have already seen in the last class. Okay. We have already seen this in the last class, that w comma p, they have bijection. Of course, see, some student is giving another method. Directly we can create a bijection. Yeah, that is also fine. Okay, let's see the method number 2. Method number 2, that is also fine. Your p, what is that? P is 2 power 0, 2 power 1, 2 power 2, 2 power 3. This is your p, right? 2 power 3. We can directly create a bijection, no problem. Okay, let's create a bijection directly. What I will do now? See, if you want to prove p countable, what I can do? To prove p is countable, because p is already infinite. P is already infinite. Remember, this p, this is already infinite. Okay, so if you want to prove that p is countable, you just have to give a bijection between n comma p. You just have to give a bijection. Okay, there exists a bijection. Just give a bijection between p and n. Okay, so let's see. Can you give a bijection? Yes, very easily you can give a bijection. This is your n, this is your p. Okay, so 1, 2, 3, 4, and so on. This is 2 power 0, 2 power 1, 2 power 2, 2 power 3, and so on. So you can just give this one-to-one correspondence. Consider this one-to-one correspondence. This one-to-one correspondence you consider. Tell me what is this? This one-to-one correspondence you consider. This one-to-one correspondence. So from n to p, I am giving this one-to-one correspondence. Fn equal to what? That is, what is the image of n? Fn equal to what? What is the image of n? That is 2 power n minus 1. Okay, 2 power n minus 1. You can check, this is bijection. You can easily notice this is one-to-one correspondence. This is one-to-one correspondence. So that's it. So there exists a bijection. So we have created a bijection. So there exists a bijection between p and n. And what that means? Bijection between p and n. What that means? That simply means they have same size. They have same size. Okay. And if they have same size, that simply means p is countable. P is countable. So that's it. This is enough for the countability. I hope you understood all these things. Okay. I hope you understood. Please tell me, so far, did you understand all these things? Let me know. So far, everything is clear or not? Please let me know. Let me know. So remember, if you see the levels of infinity, then where do you have this countable set? If you see the levels of infinity, in the levels of infinity, this countable infinite is the lowest level. Yes or no? The lowest level, let me tell you. The lowest level is your countable infinite. Let me tell you, this lowest level of infinity, here, on this lowest level, you have countable sets. countable infinite sets. You have countable infinite sets. And what are the countable infinite sets? So on this lowest level, what you have? Tell me. On this lowest level, what you have? On this lowest level, you have integers also, natural numbers also, whole numbers also, your P also, your E also. All these sets are there. Yes or no? All of them you have on the lowest level. Is this clear? And all of them, they have same size. They have same size. So remember, this is the lowest level. And remember, I can say all of them have same size. So can I say that if you have two countable infinite set, they have same size? Please tell me. If A, B are countable infinite, then can I say they have same size? Let me know. Countable infinite. If A, B are countable infinite, then can I say they have same size? Then can I say they have same size? Please tell me. Then their size will be same. Their size will be same. Yes or no? What is the proof? If you want to prove it, what is the proof? Let me know. If you want to prove it, what is the proof? Tell me. The proof is simple. Because they are countable infinite. Yes or no? Because they are countable infinite. Since A is countable infinite, so that means this will happen. And B is countable infinite, so this will happen, right? Agree with me? Yes or no? Because they are countable infinite, so this will happen. So this will happen. And from here, you can easily notice that they have same size. So if A, B are countable infinite, then they have same size. Agree? Please tell me. Then they have same size. So all of them on this level of infinity, on the lowest level of infinity, all of them, they have same size. So you can notice. Yes or no? Please tell me. Did you understand? Okay. Every set on the lowest level of infinity that has same size. So this is the simple idea. Okay. So if A, B are countable infinite, then they have same size. Okay. Let's see this question. Let's see this question. So tell me the answer for this question. Let's assume sigma is A. That is unary alphabet. That is your unary alphabet. Prove that set of all strings. What is set of all strings? What is that? Set of all strings. What is that? That is sigma star, right? Yes or no? That is sigma star. Prove that sigma star is countable. How to do that? How to do that? Tell me. Remember, sigma is given to you. This is the unary alphabet. What will be sigma star? Just tell me sigma star. Just tell me what will be sigma star. Sigma star will be A power 0, A power 1, A power 2, A power 3, A power 4. Yes or no? Now, how to prove that this is countable? How to prove? How to prove that sigma star is countable? Let me know. Please tell me. How to prove sigma star is countable? To prove sigma star is countable, just give a bijection. Just give a bijection. This is already infinite. This is already infinite set. Okay. So if you want to prove that this sigma star is countable, what you need to do? You need to prove that they have same size as set of natural numbers. This is what you need to prove. You need to prove that they have same size. And for that, you need to give a bijection. You just need to give a bijection between n and sigma star. Can you give a bijection? Let me know. 1-to-1 correspondence. Can you give 1-to-1 correspondence between n, sigma star? Can you give 1-to-1 correspondence between n, sigma star? Let me know. Yes, very easily. Yes, quite easily you can give 1-to-1 correspondence. This is your n. This is your sigma star. Okay. So can you give a 1-to-1 correspondence? Sigma star. This is sigma star. This is your A power 0, A power 1, A power 2, A power 3, A power 4, and so on. And this is your n. That is 1, 2, 3, 4, 5, and so on. So tell me, can you give me a bijection? Can you give me 1-to-1 correspondence? I want 1-to-1 correspondence. Can you give me 1-to-1 correspondence between these two sets? Between these two sets, can you give me 1-to-1 correspondence? Yes, consider this 1-to-1 correspondence. Consider this 1-to-1 correspondence. So your 1-to-1 correspondence, you can notice from n to sigma star, from n to sigma star, you can give me this 1-to-1 correspondence. What is Fn? That is A power n minus 1. Fn is A power n minus 1. You can check this is bijection. You can check this is bijection. You can check this is bijection. And because this is bijection, so what I can say? So size of n, that is same as size of sigma star. Size of n, that is same as size of sigma star. So sigma star is countable. Yes or no? Is this clear? Since size of n, that is same as size of sigma star, so sigma star is countable. Please tell me, understood? Let me know. Did you understand this? That sigma star is countable. Countable infinite. Of course, sigma star is countable infinite. Okay. Let's move on now. Tell me the answer for this question quickly. Quickly tell me the answer for this question. Set A is called countable infinite. What is the definition of countable infinite? Set A is called countable infinite if and only if. What is the definition? What is the definition? All of them. Because all of them, they have same size. Yes or no? All of them, they have same size. Agree? See, all of them have same size. Yes or no? See, how can you say that? Okay, notice. All of them have same size, right? I told you on this level of infinity, all of them have same size. See, okay, for example, let's see this. You can notice that. If you have a, you already know that this has same size as integers. They have same size. Yes or no? They have same size. So tell me, now you just tell me this point. If integer size is equal to a size, then can you say A is countable infinite? Then can you say A is countable infinite? Of course. Yes or no? Because if this will happen, then what will happen? Then this will also happen. Then this will also happen. And then this will also happen, that as A is countable. A is countable. And can you notice the reverse direction will also happen? Can you notice the reverse direction will also happen? Yes or no? Is this clear? Please tell me. So remember, see, initially we defined, see, notice. Initially we defined countable infinite in this term. Okay. But actually you can define in any of them, in terms of any of them. Yes or no? Because ultimately they have same size, right? Set of natural numbers, set of integers, set of whole numbers, they have same size. All of them, they have same size. Agree? Yes or no? All of them have same size. So you can define this countable set in terms of any of them. Is this clear? Please tell me. For understanding purpose, in the beginning, we were defining like this. But if you notice, now because we know that all of them have same size, so we can define in terms of any of them. So this is the idea. So you can notice that all these definitions are correct. For example, set S is countable. Set S is countable if and only if, set S is countable if and only if S is finite, or there exists a bijection between what? Tell me. See, set S is countable if and only if S is finite, or the size of S is same as size of N. This was our definition. Do you agree with me? Do you agree with me? This was our definition. This is the definition of countable. Now tell me, you already know that this is same as size of integers. Can I say this is same as size of integers? Tell me, can I say this is same as size of integers? So I can put that also. Yes or no? Because we already know that has the same size. They have same size. So you can define like this also. So you can define like this also, because they have same size. Is this clear? Please tell me. Let me know. Okay. Is this clear? So remember this simple point. Every set on the every countable infinite set have same size. Yes or no? Every countable infinite set, they have same size. Agree? Please tell me. Every countable infinite sets, or I can say all countable infinite sets, have same size. All countable infinite sets have same size. have same size. So you can define with respect to n, with respect to z, you can do whatever you want. Okay, this is the first point. What was the second point? That countable infinite is the lowest level of infinity. Yes or no? Countable infinite is the lowest level of infinity. Is the lowest level of infinity. Is the lowest level of infinity. Countable infinite, that is the lowest. That is the lowest level of infinity. What that means? Let me tell you. Let me ask you one question. So let me ask you one question. If S is infinite, if S is infinite and size of S is less than equal to size of n or integers, then tell me, then what you can say about size, then what you can say about S? Then what you can say about S? Tell me. Let me know. See, S is infinite. S is infinite, but the size of S is less than equal to size of n. But this is the lowest level of infinity. You already know this is the lowest level of infinity. You already know this is the lowest level of infinity. So what you can say about S? S is countable infinite. Very good. Very good. S is countable infinite. S is countable infinite. And that means what? S is countable infinite. That means what? That means size of S, that is same as size of n, that is same as size of integers, that is same as size of whole numbers. All these things, all of them, they have same size. Yes or no? So very simple. So this is the idea. I hope you understood. Now let's see this question. Tell me the answer for this question quickly. Tell me the answer. So what is the answer here for this question? For this question, the answer will be set A is called countable infinite if and only if there exists a bijection between n, I. That is correct. This is also correct. This is also correct. This is also correct. Because all of them have same size. Yes or no? All of them, they have same size. Agree? Okay. All of them, they have same size. Let me ask you one more question. Let me ask you few more questions. For example, instead of bijection, if I say injection, instead of injection, instead of bijection, I am saying injection. Now, is this statement true? Think about it. Now, which statement is true? Set A is countable infinite. Tell me. No, this statement is not correct, right? Because S can be finite. Okay, in this situation, these statements are not correct. Okay, all of them, because these are not correct. Why? Because remember, maybe S, C. If you have this, then does it imply S will be infinite? If you have this, does it imply S will be infinite? If you have this, if you have injective function from A to N, does it mean A is infinite? No, A can be finite also. Yes or no? Agree with me? See, if you have this, then from here, I can say A can be finite or infinite. A may or may not be finite. A may be finite also. A may be finite also. For example, see, very simple point. If I give you this set, if I give you this set, and if I give you this set, is there an injection? Tell me. Is there an injection? Let me know. Yes, this is the injective function. You can notice this is the injective function. Is this clear? So you can notice there exists injective function. Please notice there exists injective function from A to N. There exists injective function from A to N. Yes or no? There exists injective function from A to N. This means A can be finite also. Okay, this means either A is finite. Okay, remember, this means either A is finite or what will happen? Tell me, either A will be finite. If you have injective function from a to n, if you have injective function from a to n, this is the definition of countable. See, this is the definition of countable or not? Please tell me. This is the definition of countable, not the definition of countable infinite. This is the definition of countable. Is this clear? This is the definition of countable. This is not the definition of countable infinite. This is the definition of countable. Or I can say that either A is finite or A is countable infinite. Either A is finite or A is countable infinite. Okay, so please understand that why this statement is false. Let me know. Let me know why these are false. See, I am saying all of them are false. Why? Because this is the definition of countable. Yes or no? Remember, this is the definition of countable. This is the definition of countable. This is not the definition of countable infinite. The question is asking for countable infinite. Did you understand? Let me know. Did you understand? For example, this is also the definition of countable. This is also the definition of countable. This is also the definition of countable. All of them, they are definitions of countable. They are not the definitions of countable infinite. Did you understand this? Please tell me. All of them are definitions of countable. But the question is asking countable infinite. The question is asking countable infinite. So all these statements, they are wrong. Is this clear? You can see. Please tell me, understood? Did you understand this question? Let me know. Okay, so let's move on now. So remember this simple point. Again, I'm telling you, please don't make a mistake. What is the definition of countable? The definition of countable and the definition of countable infinite. Countable infinite. What is the difference? Let me know. What is the difference? Countable simply means that set S is countable. When can I say? When can I say set S is countable? When can I say set S is countable? If and only if there exists an injection. If and only if set S cardinality is less than equal to set N cardinality. Yes or no? And when can I say S is countable infinite? And when can I say S is countable infinite? If and only if set S cardinality is equal to set N cardinality. Yes or no? Set S cardinality is equal to set N cardinality. Now remember this point, that this means there exists an injection. This means there exists an injection from S to N. Okay, this means there exists an injection from S to N. This means there exists a bijection from S to N. Okay, is this clear? So this is the simple idea. Now tell me the answer for this question. In the same question, if I ask you countable only, now tell me, now which option will be correct? I am asking only countable. Set S is countable if and only if. Yes, very good. Now all of them are correct. This correct, this correct, this correct. All of them are correct. Very good. Very good. Okay. So these are some points. I hope you understood all of them. Okay. So now let's move on now. Tell me the answer for this question quickly. Tell me the answer. Is this true or false? Set A is countable if and only if set A cardinality is less than equal to set N cardinality. Yes, this is true. Yes, this is a true. Okay. What about this statement? Is this true or false? If set A is infinite and there exists injective function from A to N, then can I say it is countable infinite? Yes, this is also true. Okay. So these statements are true. Very simple, brilliant. Okay. All of you have given correct answer. Okay. So that's it. So this is what we have seen. This is your countable set. We have done, I think, enough practice we have done. Okay. More practice we will do in future. But so far, did you understand? Now, in the next lecture, we will study uncountable set. But tell me, did you understand this lecture? In this lecture, everything we have seen, did you understand? Please tell me. Everything that we have seen, did you understand? Let me know. Let me know. Anyone has any doubt in this? Anyone has any doubt in this? Is there anyone who has any doubt in this? Remember one thing I told you, the lowest level of infinity, we denote by LF0. Yes or no? We denote by LF0. So this lowest level of infinity, I told you, this lowest level of infinity was denoted by LF0. This symbol, this type of symbol is there. Okay, you can just check it out. This type of symbol is there. This symbol is called LF0. LF0. Or I can say LF null. Okay, so this symbol is called LF null. The lowest level of infinity was denoted by this symbol by Cantor. By Cantor. Okay, by Cantor. So if anyone asks you, so this is the summary. Let me tell you that we have seen so far what we have seen. So this is what we have seen. And we have proven also. We have seen that set of natural number, size of set of natural number, that is same as size of integers, that is same as size of whole numbers, that is same as size of E, that is same as size of P, all these things. Okay, that is same as size of sigma star, all these things. And what is that? The size of the lowest level, the size of the, I can say, countable infinite set, that is denoted by this symbol. This is symbol. This type of symbol you have, you can just check it out. Okay, so this type of symbol you have, LF0. Is this clear? If anyone asks you what is the size of natural number, then what you will say? What is the size of natural number? What you will say? Just say LF0, LF null. Just say LF null. LF null. Okay, size of integers, that is also LF null. So this is just a small point. No one will ask you, don't worry. Okay, don't worry, no one will ask you, but this is just a small point that this, I can say, the lowest level of infinity. You can say this countable infinite set. Countable infinite set, that is denoted by LF0. Is this clear? Countable infinite set. So remember this point. If S is countable infinite set, if S is countable infinite, countable also, infinite also. Okay, if S is countable infinite, then I can say size of S is equal to LF0. LF null. Okay, and I don't know how to create this symbol, but you can just check it out. This type of symbol you have. Okay, this type of symbol you have. So you can just check. So if S is countable infinite, then size of S will be LF null. So from here you can easily notice that all countable infinite set have same size, yes or no? Agree or not? So all countable infinite set have same size. All countable infinite sets have same size. Okay, have same size, and that is your LF null. Okay, so I should learn how to create this. Okay, but anyway, that is LF null. You can check this symbol. You can just check it out. LF null. Okay, is this clear? Please tell me. So you can see all countable infinite set, they have same size, and that size is LF null. Okay, so that's it. This is your chapter. So we have seen what is countable infinite, every variation, every definition, some examples, more examples we will see in future. Don't worry. Okay, some more questions, some more examples, some more theorems we will see in future. But in the next lecture, we will study uncountable set. Okay, this chapter we will study uncountable. Which set are uncountable? This is what we will study in the next lecture. Okay. Thank you, everyone.